Hi, my name is Roni from nVidia. Today I want to discuss with you about OVS Benchmark, maybe a fresh view. I'm here together with Guy. So the agenda, we're going to talk about common practice today in testing switches, which basically, as you can see in the pictures, focusing on worst case scenario or best case scenario. Then I'm going to talk about network traffic pattern, mainly elephant flows and mice flows and TCP locality. Then we're going to suggest a new way to extend the benchmark, and we are going to show how we did that test or prototype of that test and some results. So switch benchmarks. Today there are few RFCs for testing switches, RFC 2544 and so on. There's also VSPERF, which is telco testing tools. And the tests are usually focused on one of the two. They are both worst case scenario. Using a fixed packet size, like choosing 64-byte packets or 128 and so on, and then choosing a concurrency. When the concurrency is chosen according to the tested scenario, if you're a switch, you're going to test MAC addresses, different MAC addresses that you're going to have. If you're using underlay, it's going to be the number of VXLAN VNIs or peers. If it's connection tracking, it's going to be a number of TCP sessions and UDP sessions. The packets are sent in a round robin, means that you're sending a packet per flow, and if you have a high concurrency, you are not going to benefit from any cachings and going to get to the worst case scenario. There's another type of packet choosing. It is called intermix or iMix, and when there is a specific mix of packet sizes and order, and usually that should fit the working point you want to measure, but still the traffic is random. So usually the argument is if I can run worst case, then I'm good in the common case. Isn't the truth? So we have to look about what we are testing the worst case for. For example, when you're testing 64 bytes packets, we are not going to stretch the PCI. Okay, we're going to stretch the NIC maybe. What's going to be the blocker is the pipeline in the NIC, but not the PCI. When we are testing a max MTU size, we're going to stretch the PCI, mainly if we're looking on 100 gig. When you have a Gen 3 PCI, which is a little bit more than 100 gig, you're going to stretch that PCI. This might be your bottleneck. We also know that different packet sizes in software mainly are going to have different processing time, and also when you have a big packet size, usually you have a little bit more time between packets to process them, and small packets you have less time to process the packets, and this is going to affect the overall performance. A different angle of looking of that is the 100 gig or today that we have starting to see in the market 25 gig, 50 gig, 100 gig NICs. When we are looking on the numbers that those NICs can generate, like in 64 bytes, it's going to be 148 million packets per second. And we're looking on software of OVS with VXLAN and connection tracking can do around 500 kilo packets per second. If it's an optimized OVS, for example, some customers are cutting corners to make it more specific for their needs and make it more optimized. Still, it's not going to be more than 2 million packets per second. And this means that if you're running software, you're going to have to allocate 50 to 100 cores if you want to support 64 bytes, right? And obviously, you're not going to do that. So you're testing a scenario that is not your common use case, and you're not seeing what's going to happen in your system. Okay, the area of networking or network behavior was studied a lot in recent years. I'm going to show you a few papers and focusing on elephant mice flows and locality. So in this paper, the authors, they have public traces that were taken on ISP network. And what they did, they split the traffic into TCP or UDP flows, 5 tuple, and then they measured the number of bytes that were exchanged between the peers in the traffic, and they sorted the flows from the biggest flow to the smallest flow in bytes. After that, they set a bar. For example, in this case, 10 kilobytes, and so how many flows were bigger than 10 kilobytes? And looking at the percentage, you can see that it's a very low number of flows, right? 7% on the first record and 6% on the second record. So most of the flows, 93% of the flows are less than kilobyte in this case. When you set the bar a little bit higher, the number of flows, or the percentage of flows that consume more bytes, then the bar is very small. You can see in 5 million bytes, it's a fraction of a percentage in both records. Now, interesting to look on the bytes. When you're looking on the bytes, you can see that even that only 7% of the flows were more than 10 kilobytes, they consume 95% of the bytes. This means that if I can, for example, if I can classify only the big flows, only the 10K flows and above, I still can classify 95% of the bytes. If I can optimize them, if I can do anything on this small amount of flows, the benefit will be very big, or we will see the impact on the system because some of the bytes belong to those flows. Another interesting paper, the authors took traces from different data centers. The data centers were of different types. The application were very different. The web services, file storage, business, and so on. Even data intensive, like indexing using MapReduce. They also have different type of data centers. They were commercial, they were private, and they were campus data centers. And again, they saw that most of the flows are less than 10 kilobytes, and 10% of the flows consumed almost all the data. Another interesting thing or behavior is that even when the concurrency was high, like you have 1 million flows, or I don't know, 100K flows, looking on a second or less than a second, only a fraction of those flows are really active, are really sending packets. In this paper, the authors looked on the same data centers, but they took traces with a difference of 5 years between them. And amazingly, they saw that the behavior was not changed so much. Long-lived flows consumed most of the traffic again, and that haven't changed. They saw that long flows are now longer and bigger, but this is really amazing because think of it, how many different applications you have in 5 years, and how technology changed, the web, how you build web pages and videos and so on. And the last one I want to show is was done only for social media. And again, we see that most of the flows are short. They see here they looked on the millisecond level, and they saw that during a millisecond, only 15 to 30 flows consumed more than 50% of the bytes. So caching can help here for sure. Now I'm going to talk about locality. Looking on the big flows, you need throughput to pass a lot of bytes. When looking at TCP, you have the window size. You must have a big window size. This means that when a client sending ACK to the server is saying, I got all the sequence until here, the server going to send a burst of new data. It's not going to send a packet. There's no ACK for single packets. The packets are sent in burst. And this is because TCP nature also to optimize, to be more optimized. For example, we even have hardware offload for that, TSO. So we see here that locality fits the nature of elephants and mice flows, and locality going to be strong for the elephant flows that need throughput, and TCP generates this locality by its nature. We took also some records of ourselves, mainly focusing on locality. In this case, you see Netflix. What you can see here is that it was recorded on the client and not on the server. The server was 5 to 10 milliseconds round trip, probably cached. What you can see here that on a very small time frame, a burst of traffic was sent. We see here 8 packets in 9 microseconds, and this is on the client. So the path through the network to the client, and this was the distance between the packets. Then we can see the client is sending an ACK towards the server, and another burst of traffic in a microsecond level is sent. Again, for YouTube, we see a similar behavior. YouTube is using Twig, which is like a transport layer, like TCP over UDP. It has congestion avoidance algorithms and basically behaves the same. Again, burst of traffic within microseconds between them, every time the server getting an acknowledgement. Now looking on 100 gig, if we look on how many packets we can have, or different packets of different flows we can have on 10 microseconds, if we're looking on 64 bytes, it's around 2,000 flows. If we're looking on an average packet size like 512, it's going to be 244. This means that there are not so many flows. And if you have a locality, you're going to see it and you're going to benefit from the cache. This is how video behaves in a higher time granularity, and this is what we see that as we confirm what was seen in research, that most of the time traffic is not active. You can see that the client is downloading traffic only part of the time, only 10 to 20% of the time. This is mainly in video due to ABR, adaptive bitrate, which means that video is split to segments of the same size, 2 seconds, 5 seconds, and so on. And the client always trying to download very fast the next segment to avoid rebuffering. And if the throughput is not enough, it's going to lower the quality, and we're going to download the same segment, but with a lower quality, so less bytes. And the client will try to have this behavior that it can download the traffic very fast to avoid freezes. So most of the time, we won't see traffic at all. Same behavior for social media. Maybe because there's a lot of videos in social media. Browsing is a little bit different because in browsing there's a lot of small objects, so you are not getting to high throughput. But still, when we looked on the capture files, the locality was high. There were 2 to 6 packets within 10 microseconds, and a lot of them. And also, if we looked on the TCP UDP flows and sorted them according to the size, and we saw the same behavior, that the first 5% of the flows consumed most of the bytes. So the conclusion is that typical traffic shows a strong locality on the microsecond levels. Flows with strong locality are also the flows that consume most of the bytes. Only 10 to 20% of the consuming flows are active on a second time frame. And most of the flows are very small and ends with less than 10 kilobytes. So if we can generate a traffic that can be similar to what we saw here, we think that we can use that to optimize better our solution. For example, testing caching strategy like EMC and SMC for via software. Testing hardware offload benefit, when typically the CPU is busy with small flows and opening new flows and offloading them, and hardware will handle the large flows and also most of the packets. We can also benefit in offloading the right places in our offload strategy. And for customers, it's infrastructure planning. You probably can have maybe FPGA NIC that can support 200 million packets per second on 64 bytes. But you're not going to see that anyway, and it's going to be expensive, and it's not your traffic pattern, so you are not going to plan your infrastructure right. And this is where comes the new test or prototype of testing we want to show here.
Thanks, Roni. So I'm Guy Twig from the software performance team. Now we are going to talk about our testing. So for the topology we choose to use for the benchmark as the following. We have nVidia Bluefield 2 DPU on the device under test, connected back to back, to T-Rex is a software packet generator. In the ARM itself, in the Bluefield 2, we have OVS DPDK configured with VXLAN and connection tracking, with also hardware offload. In the VM itself, we have test PMD for the packet forwarder. As Roni mentioned before, we separated the stream for two streams, elephant stream and mice stream. The main idea is that the elephant stream holds something like 1K flows with 1400 bytes per packet size. The stream doesn't have much packets, but in overall it holds from 70 to 80% of total bytes from the stream. Also, it holds a locality number that represents the number of packets that will be in a row. This is for a better caching. Like we can see here, we have packet 1, M is the locality number, then packet 2, and so on. About the my stream, we have the my stream has many packets in overall, but holds only up to 30% of total bytes. Each my stream has many different packets with 128 bytes or 256 bytes as a packet size. For our testing, we used one elephant stream with 1440 bytes and with 1K flows and 10 mice streams. 5 mice streams with 128 bytes and 5 mice streams with 256 bytes. Each mice stream we used has 30K different packets. We can see here a calculation of how do we calculate the theoretical number of a stream with elephant and mice streams. So we have here one elephant stream with the locality 8 with 1K flows and 8 mice streams with 100K flows with 64 bytes and 6 mice stream with 100K flows with 128 bytes and 6 mice streams with 100K flows with 256 bytes. So for the total system stream sequence size, it's about 14,000 bytes. We can do the calculate here. We can see in the total bytes. And the total stream sequence has 28 packets. For the average packet size, we are getting 500 bytes. So for 500 bytes, the rate we can get, the theoretical rate we can get is 24 Mbps. In this example, we can see that the elephant stream has 80% bytes from all the streams. So for the results, we have here graph for locality versus worst case. Worst case is locality 1. Locality is what I mentioned before. We took elephant stream with 1K flows with locality 10 and 10 mice streams with 30K flows each stream. So for the worst case, we took the average packet size for this stream, for this exactly stream, and we got only 16.8 million packet per second and 88 line rate percentage. For the locality 10 with the same stream, we can see improvement of between 7 to 10% of the total throughput and bandwidth. We also measured hardware offload versus software VIRTIO. As you can see here with software VIRTIO, with the same stream I mentioned before, we can get only 1.1 Mbps with a line rate of 6% of the line rate. For the VIRTIO, software VIRTIO, we used 4 cores and it was tested over ConnectX-6 DX. Let's summarize what we had in the testing. So we could only achieve thousands of microsecond intergap and not microsecond as defined and as we see in the theoretical reviews. Still showed that small locality with 4 to 8 packets of less, it's less than 30% of the overall packets and had between 7 to 10 impact in PPS and throughput. We think that once we can generate better locality, we can reach line rate in such scenario. Setting a more realistic scenario can focus in increasing the right optimizations in the device itself. Having real case scenario can show real saving in cores when using hardware offload. In the future, we plan to combine such tests with open rate, creating full realistic scenarios like long elephant flows opening and closing and mice flows opening and closing. That's all, folks. Thanks for joining and we are open for questions. Bye.